Chapter 9 talks about logarithms and composite and inverse functions. We'll start with the latter. F of g. This whole thing means f of g of 2. And what we want to do is look at our PEMDAS, our order of operations. You always do the innermost parentheses first. So you look at the 2, and you're just trying to plug this 2 into this g. So I'm going to look over here. How does the 2 plug into the g? And I just plug the 2 in anywhere where I see an x. And that gives me f of 6 minus 4, which is 2. Now, whatever this 2 is, I'm going to plug that 2 into my f. My f is x squared plus 1. So this really becomes 2 squared plus 1, or 5. Same thing if you have g of f of 2, except I'm going to do the f of 2 first, because that's the innermost one. Plug the 2 into the f, and that gives me 2 squared plus 1 is 5. So now g of 5, I plug that 5 into my g up here. That becomes 3 times 5 minus 4, 15 minus 4, which is 11. When you look at f of g of x, then you're just not plugging a number in. You're just saying f of g of x. Well, plug x in wherever x is, it just kind of stays the same. So this is 3x minus 4. I'm going to plug that whole 3x minus 4 into this x squared up here. So that whole 3x minus 4 gets put in 3x minus 4 squared. Now, plus 1. Foil that out, so that's 9x squared minus 12, 24x plus 16 plus 1. So that's 9x squared minus 24x plus 17. And the same thing with g of f of x, which all works out to be 3x squared minus 1. Last type of problem is the inverse. So when you have f of x equals x squared plus 1, and I want to find the inverse of it, what I do is I'm going to replace the f of x with the y just to make my equation simpler. I'm going to switch the x's and the y's, and then I'm going to solve for y. So that means move the 1 over, square root both sides. So y must equal the square root of x minus 1. And that's the same as the inverse of x is the square root of x minus 1. To graph a logarithmic function, I'm just going to start plotting points in. So anywhere where I see an x, I'm going to put a 1 in, so that'll be a 2. If I put a 2 in, it's going to be a 4. If I put a 4 in, or I'm sorry, a 3 in, it'll be an 8. And then I kind of want to go the other way. If I put a 0 in, I'm going to get 2 to the 0, which is 1. If I put a negative 1 in, I get 2 to the negative 1, which is 1/2. And if I put a negative 2 in, I get a 1/4. 2 to the negative 2 is 1/4. So let me plot that. And it's going to look like this. The same vein of things, log base 2 of x equals y. Remember that this is a base. This, because logs are exponents, this is an exponent, and this is just your other number. So your base is going to be 2 to the y this time is equal to x. I'm going to make that same xy chart and just plug in things for y instead of x. So when y is 1, x is 2. When y is 2, x is 4. When y is 3, x is 8. And if you just see, I'm just switching these two numbers back and forth. So when y is 0, x is 1. When y is negative 1, it's 1/2, negative 2, it's 1/4. So when I plot it, it's going to look like that, which is a reflection about this line, which just basically means that it is an inverse of each other. To graph things e to an x power or ln of something, I'm going to need my calculator, and I'm going to find that button way down here. So this e to the x. So I'm going to press second, e to the x, and the first number that I'm going to plug in is 2. I'm just going to plug a 2 in there. It's going to look like that, and when I press enter, I get 7.389, so that's my y, 7.39. Let's round it. Going to do it one more time for the rest of these. And I get all of these points, and I just simply plot those points on my graph. It's going to look like this. Remember that e is just this number. It's about 2.72, and it's a number that we use for composite functions when we do compound interest. Let's see what it looks like with the natural log. With the natural log, I'm going to do the same thing, except I don't need to press shift this time. It's just this button right here. This is going to be ln, and I'm going to plug in 6 first. 6 minus 4 is 2, so just ln 2. That equals 0.69. We'll do the same for 5. ln of 1 is going to be 0. And look what happens when I plug in ln of 4. ln of 0, I get an error. That's because you can't have a natural log of anything that's less than 0, so 0 or any negative numbers. So I'm just going to try and get as close to 0 as I can by plugging in a 4.5, a 4.25, and a 4.1, let's say, to see what happens here. And after I plug those in, because 4.1 minus 4 is 0.1, that's why I plug these numbers in, I get these coordinates, and I'm just going to plot and those. I'm going to get something that looks like this. Heading back over to my numbers here, log base 5 of 125 is x. Remember that this is the base. Logs are exponents, so exponents are on this side. So I just rewrite this by moving this x over. So this is 5 to the x equals 125. The log will disappear. You can do this in a calculator this way, or you can say that 5 to the x is the same thing as, since 125 is 5 to the third power, then x must equal 3. For log base 2 of x equals negative 3, remember, base exponent. So 2 to the negative 3 equals x, so x must equal 1 over 8. For the next one, 4 plus 6e to the 4x equals 16. I'm going to subtract 4 from both sides first, so 6e to the 4x equals 12. Divide both sides by 6, and I get e to the 4x equals 2. Now how am I going to get this e to the 4x out of here? Well, I can natural log both sides, so that would mean taking ln of this side and ln of 2. And anytime I take a natural log, rule of powers means I can bring the power forward. And ln of e actually just turns out to be 1. Natural log of base e to the e is equal to 1. So this is just going to be natural log of 2. And if I just put that into my calculator and then divide it by 4, I get 0.173 roughly. Going to combine a couple of properties here. Log base 4. When you have the same base, you can actually combine these two things together. If you add, you will multiply these two parts together. If you're subtracting, we're actually going to divide. So you can combine this to be x plus 3 over x minus 5 is equal to 2. What do you do from here? I'm going to change this into exponential form, meaning base, exponent, answer. So this is x plus 3 over x minus 5 is equal to 4 squared. Remember, base, exponent, answer. 4 squared is 16, which is equal to x plus 3 over x minus 5. To solve, just multiply both sides by x minus 5 to cancel here. This becomes 16x minus 80. This is x plus 3. Get everything over to one side, so this is 15x is equal to 83, and 83 over 15 is equal to x. My next goal is to write all of this into a single term. First thing I want to do is change all coefficients into powers for logs. So this will be log base a of x plus log base a of y to the 1/2 minus log base a of z squared. If I'm adding again, same base means I can multiply them. So this is x, and since y to the 1/2 is the same thing as square root of y, I'm just going to write that. And minus means I'm going to put it at the bottom, so z squared is going to end up at the bottom. So that's all there is to that problem. Now I'm trying to write this into 3 separate terms, so I'm trying to split this up. Both of these are on top, so I'm going to add once I split them up into separate logs. This is on the bottom, so I'm going to subtract once I split them up into separate logs. Remember that z to the 4th root is the same thing as z to the 1/4, and I'm just going to bring all of my powers into coefficients. This is just the reverse of what I was doing in the previous problem. Log base a of y minus 1/4 log base a of z. Looking at my population growth rate problem, they give me an equation that says 10 times e to the 3.4t, where t is the time in years since the year 2000. This means that they're growing at 340% per year. This is your starting population, and this is the power by which you grow by. 340% per year, if you change that into whole numbers, that's 3.4. So if it says how many zebra mussels are currently in the Hudson River, since t is the time since the year 2000, I'm just going to plug a 13 into there. And when I multiply all of that out, I get 1.57 times 10 to the 20th. So there are, well, a lot of mussels currently in the Hudson River. Now, how long would it take for the number of mussels to reach 1 million per square mile? Well, this time I'm not asking for t, or I'm asking for t. I have p of t. So I'm going to put my 1 million in there. I'm going to divide both sides by 10 to get rid of it on this side, which leaves me with 100,000 on the left. And to solve anything where I have e to a power of something, I'm just going to natural log both sides. That way the 3.4 can come down to the front, so this is 3.4t, and ln of e, again, is just equal to 1, so all I have is a 3.4t. The natural log of 100,000 is 11.51, and I'm just going to divide both sides by 3.4 to get 3.39 equals t. So about 3.39 years to reach 1 million.